I'm making this video to help out a little with section 3.6 related rates. It's definitely one of the hardest topics that we've hit so far because it relates a lot of information so far from this course, like derivatives, chain rule, implicit derivatives, and their word problems, which in some ways can be a lot more difficult, translating kind of English to math and then being able to solve a problem. So I'm going to take you through a different example, and I'm going to do this through some steps that might help actually with all word problems. So the first thing that I usually do is draw a picture, if possible. Sometimes a picture doesn't really help. And then the second thing I'm going to do is label all my variables, my unknowns, and especially my unknown, like label what we're trying to solve for, know where we're trying to get to at the end of the problem. Then I'm going to write an equation that relates all those variables and then solve it. All right, so this is one of the first examples, this kind of boat example, and we said we were going to do this in steps, and the first step is already done for us. So here's step number 1, draw a picture, already done. So the second step is to label all our variables. And so since we have this triangle already in the picture, I'm going to label some of the edges of it. So I'm going to label the horizontal one as X, and I'm going to label this vertical one as Y, and then I'm going to label this rope as Z. So let me dig through the problem now, and now that I've labeled some variables, see what I can find. So it says that if the rope is being pulled in at a rate, okay, so rate, that's with respect to time, and the rope is this variable z. So what that means is that the rate of change of z with respect to time is that 4 feet per second. How fast is the distance between the dock and the boat? Okay, I'm going to stop right there and read it again. How fast, that's a rate, that's with respect to time, is the distance between the dock and the boat. Okay, distance between the dock and the boat, that's x. And so how fast is x decreasing? Okay, so we should get a negative number, but this is our question. What is going on here? How fast is that distance decreasing when it is 4 feet from the dock? So when the boat is 4 feet from the dock, so that's when x is equal to 4. All right. Now, one thing to notice in this, and this is kind of an important thing to notice, and I'm just going to kind of do a little star with red here, is that these things are changing. So this boat is being pulled in, and that means x is changing, and that means that dz dt, that rate is also changing, because that dude could be pulling the rope faster or slower at any point, but right at some instant it's going 4. At the instant when it's 4 feet away, he's pulling at a rate of 4 feet per second. But again, he could slow right after that, so that's changing. Now, something that's not changing in this is that y. That is constantly 5. This guy is not lowering and raising the rope at all. He's keeping it at a constant 5. That's labeled in the picture. All right, so next let's come up with an equation for all of these variables, and we have this equation of a triangle. X squared plus y squared is equal to z squared. So we're gonna use that equation. Now, the other thing that I like to do at this point is put in anything that is constant. Now, you have to be careful here. Make sure it's actually constant, not changing at all. And the only thing that is not changing here is that y equals 5. So I can put that into this equation at this point. X squared plus y squared is 25 is gonna equal z squared. Okay, that is an equal sign right there. All right, so next step is actually to solve this guy. So we're going to take a derivative. Now, we want these derivatives with respect to time, and so that means because we have x and z, we have to use implicit differentiation. So I'm going to take a derivative with respect to x. But then, because I took a derivative with respect to x, I've got to, this is implicit differentiation, or the chain rule, kind of using both in there. I'm going to multiply it by x prime, or dx dt, because we want that derivative with respect to time. plus the derivative of 25 is 0. The derivative of 2z is z. And again, we need to apply implicit differentiation. All right, and now I think we're ready to plug in what we know. 2x, we know x is 4. dx dt, now that's our big question mark that we're going to solve for, is equal to 2, z. Now, we don't have z written up here, but we really can find z because what we have is a length of 4 and a height of 5, and then we can find that z by taking the square root of 4 squared, which is 16, plus 25. And so, what is that? 35, 41. So square root of 41 is z, and then dz dt was given as 4. So our dx dt is equal to, let's see, I'm going to cancel those 2's. Ooh, I'm going to cancel some 4's. And so dx dt is going to equal square root of 41. And we could plug that into a calculator, but I don't have one in front of me. All right, next problem. Oh no. Gold balloon, I'm not going to draw a picture because I'm not sure there's a point in drawing a picture of a sphere. Maybe later that might help, but for right now, I am not going to draw a sphere. So the second thing, labeling variables, the radius of a balloon is increasing. Okay, radius increasing. So that means a rate of change of radius right here. So radius increasing rate, that's a derivative. So we've got the derivative of the radius is 0.5. Do you know what? I just realized in that last video that I should have had negative 41. I'm just going to point that out right now. Sorry. I'm not sure why that just popped into my head. Probably because I just saw increasing here, and I know the last one was supposed to be decreasing. All right, so you can go back and change your answer on the page before to negative 41. All right, sorry about that. Moving on. The radius is increasing at 0.5 centimeters per second, and we want to know how fast is the volume changing. Okay, volume changing volume with respect to time. How fast? There's our question mark. When the radius is 7.5 centimeters. Okay, so if those are all of our variables, and notice how slowly I read through the problem, and then I kind of was reading it multiple times. That's really what it takes. Okay, so the third thing is I want an equation to relate all this. I've got volume, and I've got radius, and I've got a sphere. All right, let's write out the equation of the volume of a sphere with the radius in there. So the volume of the sphere is 4/3 pi r cubed. And so now to solve it, I need to take a derivative because I want dv dt in there. So I'm going to take a derivative with respect to time. The derivative here, bring the 3 down. It's going to cancel with that 1/3. 4 pi r, and then 3 minus 1 is 2. And I just took a derivative of r. That's not t, so I need to multiply by dr dt. And now I can plug in my variables. 4 pi, the radius is 7.5, dr dt is 0.5. Plug that into a calculator, and we're done with that one. All right, next problem. All right, so on this problem, we first of all have this. I'm going to draw a picture first. We have this 6-foot tall man, and he's walking towards a street light that's 15 feet above the ground. All right, so we have this guy, and he is 6 feet tall, and he is walking towards a 15-foot. So those little marks there are feet marks, not derivatives. He's walking towards a 15-foot tall lamppost, and he is walking towards it. And so this distance right here, how about I'll call it x. And, you know, I'm just going to start number 2 right now, because if it's a rate, then that is a dx dt, which is equal to 6 feet per second. And so he's going that direction at 6 feet per second towards this light pole. At what rate is the end of the man's shadow? Okay, so what's happening is this light post is going from here, and it's casting this shadow. And so here's the end of his shadow. His shadow is really right here. There's his shadow. And it wants to know at what rate is his shadow. And so that's at what rate, I'm going to call this S for shadow. And so we want to know the rate, ds dt. That's an S right there, ds dt. I think what's really tricky about these problems, what trips me up a little bit, is that I always want to call this distance right here the shadow, but it really is talking about what these problems actually are asking. And to me, it's not perfectly clear that they're asking this, but they are asking for the rate of change that the tip of this shadow is moving with respect to the light post. And so that to me is always a little bit confusing, but that is what they mean there. And so let's see, let's read the rest of this problem. So where are we? At what end is, or what rate is the end of the man's shadow? Okay, that's that guy. When he is 8 feet from the base of the light. Okay, 8 feet from the base of the light. So that means that x is equal to 8. All right, so there's number 1. We drew a picture. There's number 2. We labeled a bunch of variables. And now let's come up with an equation. So we need an equation that has a ds dt and a dx dt, and so that means we need an equation with s and x in it, and we can do this through triangles. So I'm going to use some similar triangles. I'm going to first of all go for the big one. So I'm going to go height of the big one, base of the big one. So that is height of the big triangle, base of the big triangle. And that is going to be equal to the height of the smaller triangle and the base of the smaller triangle. So the height of the smaller triangle is 6. The base of the smaller triangle is s minus x. All right, now I know in solving this, I want to take a derivative, so I'm going to move stuff around so that everything's in the numerator and simplified as possible. So I'm actually going to take this equation, I'm going to cross multiply. So 15x minus 15x is going to equal 6s. I am now going to get all my s's on one side and all my x's on the other, so this 6s is going to move over here. So that would be a 9s is equal to, I'm going to move the 15x over to the other side just to make everything positive. Now I'm going to take a derivative because I know my knowns and my unknowns are with respect to time. So 9. Now I just took a derivative of s, so I need to multiply by ds dt because that was not a t. The derivative of 15x is 15. Now that was not a t. Alright, I'm sorry my video just glitched. I pressed something funny, so hopefully nothing too silly just happened just then. Alright, where was I? I took a derivative of 9. I multiplied by ds dt. I took a derivative of 15x. That was 15, and I've got to multiply it by dx, let's do that with a black, dx dt. And now I can plug in my knowns. So 9 ds dt is actually what we're looking for, is equal to 15. dx dt was 6. And so ds dt is going to equal 15 times 6 divided by 9, which is 10. Now, the only thing that I haven't taken into consideration here is the direction. And what I should have done for that is actually said that dx dt was negative, because this rate right here, that distance, is actually decreasing. And if we do that and then plug in a negative, that actually makes it a -10, which seems right because really this distance right here is decreasing as well. So it would make sense that that derivative should be negative with the function is decreasing. All right, hope all this helped.